Okay. All right. Yeah, welcome. Yeah, it's a great pleasure to be here. So a few years, or 1 year or 2 years ago, Kira and Galois approached me with the idea of organizing such an Arizona winter school on perfectoid spaces. And I must say that I was a bit reluctant because I thought it would be too much work, and so I backed out. And so I'm very happy that still he managed to find speakers who did this job, and I think it was really a lot of work. And first of all, I want to thank all the speakers for all the work they've already done and will do this week for their efforts. I also want to thank all the organizers for setting this up. It's a huge event. Yeah. All right, so now I'm here and I don't know what I'm supposed to talk about. So I thought as some of the first talk, it's maybe a good idea to start with some kind of prehistory of perfectoid spaces. So let's maybe, as a title, let's say some historic remarks. Should I write bigger? About the genesis of the paper perfectoid spaces. Or maybe as a subtitle. Let me put a slightly provocative statement. Why perfectoid spaces are a failed theory. You see, I'm Prussian, and if a Prussian says he wants to do something, he somehow feels responsible for actually doing it. And this hasn't completely worked out. So, all right. So, how did my work on perfectoid spaces start? In some sense, it started when. So in 2007. I came to Bonn as an undergraduate. Are there thinner pens? Because I'm... and I studied under, I think it's better, yeah. Under Michael Rappaport. And basically, by the time I came to Bonn, he gave me the following problem to think about. So this problem was the weight monodromy conjecture. Yes. Okay, so let's say X is a smooth projective scheme over the periodic numbers. Let's also fix some integer I at least 0 and some prime L not equal to P. And consider, oops, the Galois representation of the Galois group of Q's that you get on the Tal cohomology. So you have the IC Tal cohomology of your variety. I'm off screen at this point? Okay, because there's a black. Okay. Okay, great. Well, I can pull it. So, let's consider the analytic Tal cohomology of X space changed to QP bar. Okay, now I should put this here. Right? Okay. And take a new paper. Great. So, let's consider the Scholze representation. And so what is known about the Scholze representation? So, I mean, something that's actually historically quite curious is that all this perfectoid theory, which is very much tied to p-adic Hodge theory, actually started for me with some computing L-adic problem, right? So L is not equal to P. This week you will hear a lot about what happens if L is equal to P. So what is known about this? One thing is that there is some kind of weight decomposition. So let's say, to make it easier and not just have a filtration, let's actually fix a geometric Frobenius. So an element which on the residue fields acts as x goes to x to the 1 over p. So if this is such a Frobenius, then you can actually decompose V into a direct sum of weight spaces, and the weights range from 0 to 2i, where phi acts through Weyl numbers of weight j. On this piece Vj. So Weyl number of Vj is this usual thing which we know from the Weyl conjectures. It means that it's in algebraic numbers, all of whose complex absolute values are p to the j over 2. All right. So actually, how is this proved? So I think this is due to Rothbard and Sink if X has semi-stable reduction. I think that's from around 1980. And then de Jong proved this alteration theorem somewhere in 1995 or so, in general, to reduction to the semi-stable case. And there's another thing called monodromy, and then the weight monodromy conjecture is about relating these two structures. So well, strictly speaking, it goes from V to V Tate twisted by, okay, I never get my signs right, plus or minus 1. I will say what it means in terms of these subspaces Vj in a second. This is a Tate twist. Coming from the action of inertia. So it's in some sense, a logarithm of the inertia action. So this is about the action of the Galois representation of the residue field, and this is about the action of the inertia subgroup. And the conjecture says the following. Maybe I should first say that. In particular, n gives you a map from Vj to Vj minus 2 because real numbers on the Tate twist, they are of weight 2. Tate twist occurs on H2. So, so the conjecture is the following. That for all integers, the jth power of this monodromy operator gives you an isomorphism from the weight I plus j piece to the weight I minus j piece. Okay. That's this. Okay. All right, maybe some explanation for how to think about this. Some examples. Maybe at first it's surprising that in something which is the I-score homology of some smooth projective variety is somehow in this weight decomposition not pure of weight I. And that's in fact a feature of the bad reduction case. And in some sense, the weight monotomy conjecture tells you in which sense somehow it's still pure of weight I in some sense, and that this monodromy operator somehow does something non-trivial. So, okay, let's try to say this. So if X has good reduction, i.e. there exists some smooth projective X over Zp with generic fiber X, then what we're interested in is also the same as a Talc homology of the special fiber. And so here, a priori, you have an action of the Galois group. Here, you just have an action of the Galois group of the residue field. And this isomorphism in particular tells you that this action actually factors over the Galois group of the residue field. So inertia acts trivially. So this isomorphism is somehow the proper smooth base change theorem in a Talc homology. So if inertia acts trivially, we see that n must be equal to 0. Okay, now let's go back to our conjecture. The conjecture says that n to the j is always an isomorphism, but n is 0. So how can this happen? N to the j is equal to 0 is an isomorphism, so equivalently Vj is equal to 0 for all j which are not equal to I. Because if one of them would be non-zero, then, well, the zero map would be an isomorphism of this vector space. I.e., V is Vi. But this is precisely what you see from the Weil conjectures. So X over Fp is some proper smooth variety over Fp, and then the Weil conjectures tell you that on the Talc homology of it base change to Fp bar, you only this is pure of weight I. Okay, so in the good reduction case, this works. Well, you see, I changed from Vi plus j here to a Vj, so maybe I should, yeah. Sorry. Okay, so this is a good reduction case, and maybe let's do another example to see what's really going on here, because it's really about bed reduction. So let's say E is an elliptic curve mean, this x is some elliptic curve with multiplicative reduction. So if you have an elliptic curve, then either it has good reduction potentially, or it has multiplicative reduction potentially. So actually, this conjecture I stated for QP, you can state it for any extension of QP. And so you can reduce for elliptic curves either to this good reduction case or to this multiplicative reduction case. So what happens in the multiplicative reduction case is that you have the state uniformization that you can write as a quotient of GM by an action of Q, where Q is some element of QP of absolute value less than 1. So this is as rigid analytic spaces. I think this will maybe also come up somewhere this week. And using this presentation and the fact that you can compute a Tal cohomology also, well, maybe I should phrase this as rigid analytic. You can also say adic spaces. You can easily compute the Tal cohomology of this elliptic curve, and let's try to do this. So the interesting case is I is equal to 1. So of E base change to QP bar. It's Q bar coefficients. Okay, it's this. And one way to try to compute this is to use some kind of what is it called? Hochschild-Serre spectral sequence for this covering of this quotient by GM. So then we have spectral sequence which goes from I think I'm not using the group cohomology of Z acting on the Tal cohomology of GM with Q-bar coefficients, converging to the Tal cohomology of this quotient. Okay, and what is this here? This is QL bar if J is 0. It's a Tate twist minus 1 if J is equal to 1, and it's 0 else. And also the cohomology of the integers, I mean Z acts trivially, so with trivial Z action. And so you see that the spectral sequence looks as follows. You have a QL bar down here. You have another QL bar down here. You have a QL bar 1, minus 1 here, and you have a QL bar minus 1 here. Okay, and so in particular, there can be no differentials. So differentials would go like this. And so we see that actually we have an exact sequence. 0 goes to QL bar, goes to H1 et al. Of our elliptic curve, goes to QL bar minus 1, goes to 0. And so in particular, you see that up to semi-simplification, this is a direct sum of QL bar and QL bar minus 1, which looks like it's weight 2 and weight 0. Okay, so V2 is QL bar minus 1, and V0 is QL bar And the splitting here really depends on the choice of this phi. Okay? All right, but weight monodromy, in this case, predicts that the monodromy operation is an isomorphism between V2 and V0. So if it would really split as a direct sum, then it would somehow really manifestly be weight 0 plus weight 2. But it doesn't split, and so in this vague sense, it's still of weight 1. And this can be checked by hand in this case. What it comes down to is that the inertia action is non-trivial on L power roots of Q. So if you actually try to compute the first état cohomology of, well, it's an elliptic curve, so it's basically the same thing as computing the Tate module. And computing the Tate module in this quotient gm mod q to the z, someone looking for elements of gm whose L's power is a power of q, so you get some roots of L's roots of unity and L's root of q in there, and then you try to compute the Galois action. All right. So in this case, you can understand this very explicitly. And okay, that's almost as far as you can go. So the conjecture is known in dimensions 1 and 2. So dim1 uses neuron models. So for dimension 1, you can reduce to a beam varieties. Or alternatively curves. And I think you can, in either way, you can figure this out. You can either use neuron models or semi-stable models. Sorry, yeah, for I equal to 1 or 2. So if you're interested in this in some specific dimension for some specific integer I, then you can always reduce to the case that the variety is also of dimension I by somehow taking ample hyperplanes to get the cohomology. You preserve the cohomology by weak Lefschetz. So. And dimension 2 is due to Rappaport and Singh. In that same paper. Well, I mean, again, plus a, well, what? Yeah, I guess plus de Jong again. So that's one remark. The other is that it's actually known in equal characteristic P. i.e. over FP Laurent series T. Okay, and this fact is proved in Deline's VL2 paper. And it uses that L functions over function fields have good properties. By some of the usual Lefschetz trace formula business that you can reinterpret L functions as the characteristic polynomials of Frobenius on état cohomology. And then, well, it's some clever argument, but it essentially comes down to the fact that L functions over function fields have good properties. So conversely, the weight monodromy conjecture is critical to understanding the local factors of Hasse-Weyer-Zeta functions at places of bed reduction. In some sense, one can show that it's equivalent to the statement that the Hasse-Weyer-Zeta function has no poles in the region of absolute convergence. In some vague sense. I mean, of course, if something is absolutely convergent, then it shouldn't have a pole anyway. But it might be that in the region where all the good factors converge and their product converges, there's still some local factor at a bed prime which has a pole. And this should not really occur. Okay, and so in this way, it's actually, I think, one of the most important conjectures about état cohomology. Right. Okay, so that's a conjecture. And well, Rappaport's vague suggestion was the following. That you should try to reduce it to the case of equal characteristic. After some highly ramified base change. So after base change to some very ramified K over QP. Why should this help? So I think, vague idea that he had in mind was the following. So if X over OK is an integral model, and by de Jong you might even then assume that it's same as stable, of X base change from QP to K, then if you look at the special fiber, and the special fiber not in the sense of reducing modulus of the uniformizer, but just reducing mod P. So this lives over OK mod P, which, written differently, is now FQ adjoins some variable T, where T is the image of some uniformizer, modulo T to the E, where E is the ramification index. Sorry. It's the ramification index. But so if E is very large, this is almost the same This feels like it's getting more and more like the power series ring. Right? So if you could take an inverse limit over E here in any sense, then you would get something which lives over the power series ring. But of course you can't really in any meaningful sense take an inverse limit over E here, because if you make your field more ramified, then the integral model maybe also has to be modified to make it semi-stable again. They have a totally different thing, but now it lives over a larger power of t, and it's unclear to how to make this converge somehow. I mean, of course this does not really work. So, yes, even if E is large, we still need to deform this fiber product to OK mod P from OK mod P, which is this quotient, mod T to the E, to the power series ring. And usually there are obstructions to doing so. So actually, if you are in the one-dimensional case for curves, there is no obstruction to doing so. So for curves, you could make this argument work. You just deform this guy to to equal characteristic. Well, and then there's still one thing to do. Also, in the end, you have to show that this thing in equal characteristic still has anything to do with the thing we're starting with. Still, in the end, need to relate V, which is a Tal cohomology. So it's Galois action to H1 et al. Of some x prime over Fp Lorentz series T bar, QL bar, with its action of the absolute Galois group. I guess for the Galois group I should take the separable closure. I mean, where x prime over Fp Lorentz series T is the generic fiber of the deformation. And this also seems a bit tricky because there's certainly no direct geometric way of relating these two guys, which live over different fields. And there's also, it's not really clear how to relate these Galois actions either. So, in the semi-stable case, you can relate them with log geometry. Okay. So on the Galois side, this essentially comes down to the observation that if you quotient by the wide ramification subgroups, then the Galois groups are actually canonically isomorphic because you can write both of them explicitly down as an extension of Z hat by this product of ZL1s, L not equal to P. All right. But okay, so you could try to somehow work in the semi-stable case and get this deformation to run. But this seems pretty hard. And even if you have somehow a variety over the generic fiber, which is reasonably explicit, which you can control, it's much harder to control the semi-stable integral model in its properties. It usually must be much bigger. And it would be nice if one could avoid working with integral models for this. Okay, so turning these ideas in my head, I read the following theorem. Fontaine and Vintin-Berger, which says that there's a different isomorphism of Galois groups of a very different nature. In particular, one in which a lot of the wild ramification is still preserved. Namely that if you take the Galois group of the, not of QP itself, but of QP to which you join all p power roots of p, say, then again it's isomorphic to this Galois group in character. Then it is isomorphic to this Galois group in characteristic p. And in a suitable sense of the word, canonically. Always when I write canonically here, somebody insists that even the Galois group is not a canonical object. But modulus the fact that both sides are not canonical, they are canonically isomorphic. In the sense that as soon as you choose a Galois, an algebraic closure of QP, you can actually canonically produce one on the other side. And then with those choices, they are canonically isomorphic. Okay. And so this suggests that there should be a different way of relating these geometries. And I mean, I don't know, when I read this, I tried to understand why this could possibly be true. And I must admit that I couldn't really understand what was going on in the proofs. So these proofs, they all involved these Fontaine constructions, and I think it's very hard to get an intuitive grasp for what these Fontaine constructions are. So. So something like you take the inverse limit over Frobenius of the ring of integers of QP bar mod P. It's hard to understand what it means. Okay, but anyway. So later, I learned from Fontaine something even more outrageous. Namely that something similar is true in somehow a geometric case where you do some algebras over these things. So for example, it's true that if you look at the état fundamental group of the spectrum of, say, you take QP, you join all p power roots of p to it. Yeah? Ah. Too bad. And say you take some kind of Banach algebra in a new variable t, where you also join all p power roots of t. And let's say you also invert t. Then, I mean, with the same caveat about base points as above, it's canonically isomorphic to the similar thing in characteristic P. Except in characteristic P, you don't really need to join all these p power roots because Frobenius is anyway an isomorphism on états of état things. So, I mean, it induces. Like adjoining all p power roots of t, little t or big T here on this side wouldn't change anything about the état fundamental group. So, this Fontaine-Vintin-Berger theorem is really also true in some relative setups. And so, if we are trying to get a relation like here, then we certainly want to really get a relation between some kind of étale cohomology groups of some geometric objects, and so this seems like the kind of thing you want to have. So I got interested in this business, and so I read a lot of these papers of Faltings about almost étale extensions and this big book of Gaba and Ramiro on almost ring theory and things like that. And but still, somehow I couldn't, even after this, I was still puzzled even by this Fontaine, Winter, and Berger theorem. And so things really only started to resolve after I realized the following proof. Fontaine, Winter, and Berger theorem. And that goes as follows. So a different way of saying that some absolute Galois groups are isomorphic is to say that the category of sets on which they act are equivalent, or in other words, that the categories of finite étale algebras are equivalent. So what you want to produce is an equivalence between the category of finite étale QP, to which you join all p roots of p algebras, and you want to get to finite étale FP Laurent series T algebras. And again, Frobenius doesn't care about, étale business doesn't care about purely inseparable extensions, so I could make the same kind of change of adjoining p roots of the uniformizer on the characteristic p side. So this is the same as. For FP Laurent series T. All right, and so how can one relate the two guys? So the first step is something that Tate proved already in his p-divisible groups paper. Namely that any finite étale algebra over this field of characteristic 0 extends in some sense to have almost finite étale algebra integrally. So this is in a certain technical sense that I think will be also discussed somewhere. It means essentially that that whatever the ramification is, it's killed, it's not 0, but it's killed by any small power of p, so by p to the 1 over n for all n. And so this means that the good thing about this notion is that it can be transferred, it's still something interesting, even if after you mod out p. So it's the same as an almost finite étale ZP adjoin all these guys mod p algebra. You don't forget this information when you mod out p. And this is by some unique lifting property of étale covers. Finite étale algebras. I think Gortendie called it the remarkable equivalence. But in the almost setting. Okay? But now we can use this thing that this now looks like in characteristic P, namely this algebra is now the same thing as an almost finite étale. And now you're in characteristic P, so you might as well rename all the occurrences of P as T, because it's now modulo P, it's a free variable. So it's now the same thing as an almost finite étale algebra over this ring of characteristic P. And now you just reverse the steps. So you can again lift them. To almost finitely tall my hair. Algebras over this ring. And then essentially by Tate again. Well, actually, it's even easier in characteristic P. Anyway, well, the analog of this equivalence up there, you can again go to the generic fiber. So this somehow gave a way to prove the Fontaine-Winther-Berger theorem that was, in a sense, completely uncomputational, and instead all the steps were somewhat conceptual, which made it easier for me. And it somehow gave a principle of passing between the characteristics that could potentially be applied more generally. That you first have something over the generic fibers, then you extend almost to the integral level, mod out P, then it's the same thing, literally the same thing as in the eco-characteristic case. So you go there and reverse the steps. So this suggested what to do in the relative case. Namely, you find some notion of perfectoid. I will say something about the name in a second. It's just okay, something such that you would have the same equivalence that perfectoid algebras over this ring, you want them to be equivalent to perfectoid algebras, but now almost algebras over this ring with Z power over ZP. These should be the same thing as perfectoid algebras here by some unique lifting. And then you reverse the steps, and in the end you get perfectoid algebras. How was this? Okay. And at this step, you need a unique lifting property. So you need that if R is such a perfectoid algebra over this characteristic P ring, then, well, Galois tells you that the deformation theory of algebras is controlled by the cotangent complex. And so if you want that everything deforms uniquely, you need that the cotangent complex is trivial. What is the cotangent complex? Okay, and so usually the cotangent complex will only vanish if you have some kind of étale algebra. That's the usual situation where I have it. And where this is also a situation where you apply the unique lifting here. That, right. Because here it's étale, you get this kind of unique lifting. But in characteristic P, there turns out to be another reason for cotangent complexes to vanish, which is something that I had learned from Galois and Ramero's book, and which seemed very relevant in the situation where we are happy to adjoin all p-power roots of anything. Namely, so maybe this was known before, but I learned it from Galois and Ramero's book. So if S to R is a map of FP algebras, that is what's called relatively perfect, i.e. the relative Frobenius phi of R over S, which is a map from R tensor over S along the Frobenius S to R, is an isomorphism. Then the cotangent complex is 0. And the proof is actually trivial. Phi R to S is an isomorphism, but it's also equal to 0. So the cotangent complex is something that's built from differentials, and so the only identity you need here is that if you have a differential of a p's power, that's what Frobenius does, then you get this, and this is equal to 0 in characteristic P. I think this will also come up in Berger-Butt's talks again. Okay, and so with this insight, you could make this kind of argument, this equivalence of categories, work if you define perfectoid in the following sense. And let me give the most useful one. Perfectoid QP, I mean, this setup. I mean, you have notions in all these setups, and they are all slightly different, but essentially the same. Perfectoid QP, that John all these guys algebra, is and you need some topological thing because you need an integral structure. So you need to talk about what's called a uniform Banach algebra. And the only condition is that okay, this is relatively perfect. Where R circ and R is some kind of integral subalgebra. It's a power bonded. It's the algebra of power bonded elements. And so actually the second condition you can say equivalently, just that the Frobenius is surjective. Put it over here, then I think you can also read the last line. All right, and so a corollary of this discussion is then that indeed, and with the exact same definition on the other side, that perfectoid algebras over here are equivalent to perfectoid. Algebras over here. And getting this equivalence was really purely abstract. So all the steps in this equivalence were just lemmas and not a construction. But I mean, after you write this down, you realize that actually it's easy to write down this equivalence in terms of Fontaine's, explicitly in terms of Fontaine's functors. So the functor here is tends in algebra R and maps it to R flat. So for example, R flat will be the inverse limit over Frobenius of the ring of integers of R circ mod P, and then this will be an algebra over Fp power series T. I'm writing this algebra in a well, anyway, maybe I should complete all my algebras. And in the end, it turns out to be easier to prove this corollary just using Fontaine's functors. But I don't know. I felt that I could only understand Fontaine's functors after this. Okay, and so well, then you try to set up all the geometry, and actually very much related work was done at the same time by Galois and Liu. So for example, they already proved that the Berkovich spectra of R and R tilde are the same and things like this. And so you can pass to geometry. And you get corollaries such as the following. That if you take the projective space over this characteristic P field, and then you say take the étale topos of this, then this is in some sense the inverse limit. So there's a way to talk about inverse limits of topoi. Maybe they are too categorical, but anyway. Of the similar things in characteristic 0. Where the transition maps are given by the maps which send all homogeneous coordinates to their piece powers. And I should have written somewhere that I pass to the Edding space. I think things like this will be explained during the week. So in other words, you can think of characteristic P geometry as some infinite cover of characteristic 0 geometry over maps which introduce more and more P power roots of the coordinates. And now let me just give me 1 minute to come back to where this talk started. Now let's say X and Pn is your smooth projective variety for which you want to prove weight monodromy. So then you can also base change to all P power roots of unit of P, and you can still see whether the weight monodromy conjecture is true here because inertia and Frobenius are still defined in the Galois group of this thing. And so this sits inside the projective space over this field. And now, if the projective space in characteristic P is this infinite cover, then in particular there should be some kind of projection map. And let me forget a lot of the decorations I should be writing in writing this map. So I should pass to the Edding space, I should pass to the étale side, and so on. But anyway, there is some such map, and it does make sense to take the pre-image here. And so now you have your Gaussian characteristic P, and you apply Deligne's result, and you're done, you think. But then you realize, apply Deligne to this guy. But then you realize that there's a problem. This is not algebraic. So the problem is that all these maps which relate characteristic P0 and characteristic P, they are very much non-algebraic maps, and if you try to write down anything explicitly, it involves a lot of power series. So whatever this object is, it's some horrible fractal-like object. But really, how far away can it be from an algebraic variety? And the honest answer is, to this day, I have no idea. So there is an easy case that if X is a complete intersection in projective space, then in any epsilon neighborhood, so recall that we're doing some kind of p-adic analytic geometry here, so it makes sense to talk about epsilon neighborhoods. So in any small epsilon neighborhood, you take some kind of small tube around this guy, you can always find algebraic varieties of the same dimension. And that's enough to conclude. So if anybody here could please prove that in general, you will find an algebraic variety in any epsilon neighborhood of this guy, then this conjecture would be finally settled. But I also tried a lot of different things for several years, and I failed to somehow do this final step. It feels like you're almost there, but not quite. Okay. That's why I said in the introduction.
Questions for Peter?
I think about it.
It's for the recording.
Okay.
Might be useful to the future.
Okay, so I may have missed this, but when you say that it's a failed theory, are you referring to this at the end, that you don't get something algebraic?
I guess so, yeah. I mean, this whole theory was introduced, at least I introduced it, for the purpose of attacking the rate monodromy conjecture. And I failed. And so I went on into different things, but anyway. You should still, I mean, I think there's a fair point that you should judge this theory by some of what it was designed for.
Other questions?
So could you maybe just say a little more about what is it that's special about complete intersections that makes this a lot easier?
What's special about complete intersections is that, I mean, you can write as the intersection of some hypersurfaces, and so these are all given by some equations, and then you just approximate all the equations individually, takes their intersection, and then you have what you want. And so, whereas if you don't have a complete intersection, then there's some redundancy in the equations, and you somehow need to preserve this redundancy, and I have no idea how to do this.
Other questions?
Yeah, if we could end on a positive note by saying what has been achieved by Perfectoid.
Well, I think there are other talks this week, right? They will maybe say that. After all, people seem to be interested.
All right, so let's thank Peter again.